All right, let's talk a little bit today about tolerances. So what are tolerances? Tolerances are the allowable variation in the dimensions of a part. Now the question is what is exactly is allowable, right? In other words, you could say this is acceptable. So what exactly is acceptable or allowable, right? As as with most things in design, it's complicated, right? So the first thing we'll talk about that tolerances affect is cost, right? Cost. It turns out, I'm sure you'll be shocked by this, high tolerances equal high cost, right? So the smaller the variation you want in the dimensions of the part that you want to make, the more it's going to cost you, period. There's really no way to get around this. So if we were to draw a little plot here, like this, where this is the amount of money we're spending, right? And this is our tolerance. And this way is better, right? We want smaller tolerances. What's going to happen, and this is really the catcher, is it's not a line, right? Ideally we'd want something like this, right? We want to have our tolerances. It's going to cost us twice as much. No, in real life, the line looks something like this, where every improvement in tolerances costs more and more and more money, right? And this line goes on quite far. A good example of one of the highest tolerance made part ever, actually, really fun, you should look this up, is the gravity probe B. The gravity probe B has these 1 inch, it's about 1 inch, a little bit bigger than that. They're about a ping pong size ball. 1 inch spheres in them that are spherical to within plus or minus 10 nanometers, right? So these are about 3 centimeters in diameter to plus or minus 10 nanometers. It's incredible, right? It's literally plus or minus 40 atoms or so on either side of this thing. These were incredibly expensive to make, though. From what I could tell, they grew the material they were made out of, quartz, in Brazil. They were flown to Germany for further processing, just thermal processing, and then they were ground somewhere else. I mean, this is made in Europe. This is a Europe space program thing. So anyway, incredibly expensive. The whole entire project cost $750 million. There's a couple more zeros there, and these were not cheap. So they're up here on this scale right here, right? They're up here. Down here on the scale would be like whittling a piece of a stick, right? To make some part on your porch, just going along at it, all right? And the reason for this is that to get these higher tolerances requires more effort, right? I mean, to give you an example, let's look at just drilling a hole. So if you were just to manually try to drill a hole and try to get the center of that hole where you want it, this is manual drilling, you can probably do that, best case scenario, and this is really best case scenario, to 0.02 millimeters, right? So 20 microns, 0.02 millimeters. That's actually quite good. You're lucky if you can locate and place that hole to that well. If you want to improve your odds, you'll use a fixture, right? So you put a fixture on there with manual drilling. Fixture with manual drilling will get you about somewhere between half and a third better tolerances. So 0.008 millimeters, right? Now, what's the extra cost here? What's the extra cost in adding a fixture? Well, you gotta sit there and you gotta put the fixture exactly where you want it, right? So in this case, the extra cost is time, right? Time equals money. So it took extra time to make that fixture and put it in the right place. Now you can use a milling machine / CNC, and you can do a little bit better, right? You can do 0.008 millimeters, right? In this case, it doesn't take more time necessarily. What does it take? It takes more expensive equipment, so you're still spending more money, right? Still spending more money. You can use broaching. Now with broaching, what you do is you drill a smallish pilot hole, and then you literally pull this. You pull this tool through the hole, and this tool has a bunch of gradually increasing size teeth on it that gradually take out more and more material. This, you can get better tolerances. Typically you use this when you want to have very nice tolerances on the width of your hole, but it also is good for keeping it centered. In broaching, you do that, but these broaching tools are what was that, a couple dollar signs here, are very expensive. They wear out and they have to be custom made, right? So these are quite expensive, and you still have to drill the pilot hole to get it there. You have to do that pilot hole quite accurately. And you can get even more expensive and more accurate if you want to do electron beam cutting. There you can do less than 0.001 millimeter, less than 1 micron accuracy, but obviously this is going to cost you an enormous amount of money. So the point is, right, is that you can specify as many tolerances as you want. However, it's going to cost you money, right? And unfortunately, we don't have infinite amounts of money. Now, why do we care about tolerances? Why do we want to essentially specify the largest tolerance that we can handle? Well, one of those reasons is, let's change color here, is yield, right? Yield. So let's take a very, very simple example here of, let's say we have a part where we have a hole, whoops, let's make that dashed. Say we have a hole, and we have a shaft that we want to put in that hole, and the diameter of our hole is equal to 2.0 centimeters plus or minus 0.01 centimeters, and the diameter of our shaft, we'll call it diameter 2, is equal to 1.99 centimeters plus or minus, let's say 0.02 centimeters, right? The question before us is, what percentage of our assembled parts will function, right? Now, in real life, you probably don't want this shaft too much smaller than your hole, otherwise it'll wiggle a lot. We're not even going to care about that today. All we're going to care about is, will our shaft fit in the hole? Now, this, if we remember, we always state our assumptions as clearly as possible. One, we will assume that our parts have a Gaussian distribution of size. A Gaussian size distribution, right? So the diameter of this shaft has a mean of 1.99 centimeters and a standard deviation of 0.02 centimeters. Same with this hole, okay? If we do that, then we can use a tool called statistical interference. And this is a tool that can tell us essentially the interference between two statistical distributions, right? Because our parts have statistical distributions. If we make 100,000 of these, they'll fit the sizes of these things. We're assuming that the size of these things, this is 2 centimeters, will form something of a nice Gaussian distribution around 2 centimeters and, well, a little offset, but wider. And this is 1.99, right? So statistical interference tells us that. Whoa, I skipped ahead there. Tells us that it tells us that the difference between these two statistical distributions can be found by subtracting the means of these two distributions. So our mu nu is equal to mu1 minus mu2, and the standard deviation of our new distribution is equal to sigma 1 plus sigma 2, right? So if we do this, what do we find? We find that our new mean is equal to 0.01 centimeters, right? This is essentially, right, the difference between our two means, 2 minus 1.99. And our new distribution, sorry, not mu, but sigma nu is equal to 0.03 centimeters, right? So now the variation in the difference between our two dimensions is, we can plot this. Let me just draw it, but we can plot it. Here's 0, and it's a distribution, a Gaussian distribution that's a little north of 0. Its mean is at 0.01 centimeters, and its width is 0.03. So knowing this, what is our yield? Now, what I'm curious about is, what did you guess up here, right? Versus what do you see when you see this distribution? It turns out our yield is 36%. If you add up all of this stuff and divide it by the total, or sorry, here's all of our working parts are all of this side of our distribution, where our difference is greater than 0, and our non-working parts are where our difference is less than 0. So our yield is actually not 36%. Is 64%, right? This amount here is the amount that has succeeded. It's 64% have won. So that means 36% have failed, right? Which is terrible amount of wasted material, right? Wasted material. So how can we make it better? Is really the question we have to ask ourselves. What can we do to improve our yield? Well, one, we can change our diameters. Whoops. We can change our diameters. So we can make sigma, we can change our diameters. We can make our first diameter 1 equal to 2.05 centimeters. And then our yield, our percent yield will be equal to 98%, right? Which is a lot better. But what have we done? We've increased the amount of difference between our two diameters, and we've probably made a lot of wiggle room in there, which may or may not be good for the purpose of this part, right? The other thing we could do is change the manufacturing process. We can change sigma 1 and make it 0.00. What do we say? 0.02, right? We can change the way we drill it. We can change sigma 2 possibly. Maybe we bought the shaft from somebody. We can buy it from a better manufacturer and make it smaller. So there's lots of things we can do to improve our yield, and this is actually a huge area that people work at, spend a lot of effort on. I don't know if you've heard the term Six Sigma right? 6 sigma. But the idea with that is to use use tolerances if you're manufacturing stuff, but use basically statistical inference to try to make sure that your yield, whenever you do something, doesn't matter if you're making a part or if you're doing a service industry, you want to make your percentage of happy customers, successful purchases, anything, right? Any kind of thing. You want to make your successes, your yield, 99.99966%, right? So when you compare that to our yield for our little guess, we have a lot to improve, right? And this is why tolerances are so important. If you get them right, you can ensure that you can get a high yield like this, right? If you don't, what you'll find is that stuff does not go well and you waste your company lots of money. Okay? Another important thing to keep in mind, especially as you're working on your project, is that dimensions and tolerances are linked. All right. Let's say we have this part right here where we have just a piece of material that we're trying to drill 2 holes. Here's hole number 1, and here's hole number 2. 2. All right. Now, let's say all we care about at this moment is the x direction. Let's just say, we're not even going to worry about height. Let's just worry about x. There are 2 ways that you could dimension these 2 holes, right? Let's say here's our 0, 0. Here's our 0, 0. Here's our datum, right? This is where we're measuring our dimensions from. The one way we could do it is we'll give this dimension right here. We'll call this D1, and then we'll give this dimension right here. We'll call this D2, right? And another way we could do this is we could say this is D1, and then we can measure all the way from this line here, and here is D2, right? So the question before us is, which is better? Which, with the respect to tolerances, which would we prefer? All right. The answer is, for the most part, almost entirely, we would prefer, well, obviously I made it green, right? A little bit of a hint there. The green method, right? And why is that? Why is that? Well, let's say our hole number 1, its x position, we want its x position, x to equal, I don't know, let's just make something up, 2 centimeters, plus or minus 0.002 centimeters, okay? And then we want hole, so that's D1 actually, D1. We want D2 to equal, we measure D2 to be 4 centimeters plus or minus 0.002 centimeters. What are the actual tolerances on the location of hole 2 if we use our red method? Well, the actual tolerances are the tolerances on our x that we measured here, and the tolerances added to that for our D2. So it's actually, right, our total tolerances are going to be 0.004 centimeters in the end, right? Our hole 2x is going to be equal to plus or minus 0.004 centimeters, which is bad, right? Not necessarily bad when you only have 2 of these holes, but let's say you have 4 or 5 holes and you just chain these dimensions along, and you tell the machinist, because you're going to give these dimensions to a machinist, you're going to tell him, hey, measure this hole, drill it, then measure this hole off of this hole. And he's going to do that, and by the end he might be off by a tremendous amount. However, when you measure using the green method, this is the red method here, right? When you measure the green method, you don't have that problem, right? The tolerances on hole 1 are 0.002, and the tolerances on hole 2 are 0.002, right? You don't get this cascading. At least that's what I call it, cascading of dimensions, right? So be very aware of cascading tolerances. So as you're designing and building these parts, what are for your design project, what are the couple of things you need to be worried about? One, what are the machining / material tolerances you are capable of? For the most part, you guys are going to be making these things, unless you're being funded by a company, right? So if you're making things, what kind of tolerances can you achieve when you're, say, drilling a hole or milling an edge, or let's say you're using the CNC machine, right? What kind of tolerances is that capable of? And notice I say material here because the type of material matters, right? If you choose a very hard material and you're a terrible machinist, you can get kickback on the material, which will cause your bit to bend, and you'll change your tolerances, right? So it's a function of the material, how good a machinist you are. It's quite complicated, but you should try to estimate what are the tolerances you are capable of. 2, what tolerances do you need to achieve your functionality, right? What tolerances do you need for your device to work? Now, for the most part, most of your dimensions, honestly, it's not going to matter, right? But there will be a few key dimensions where it does really matter, right? Let's say you have to put a shaft inside of a hole, right? And that hole is meant to stabilize that shaft. Well, then your tolerances do matter. If you have a huge gap in there, your shaft's going to just have not much stability, right? And if your tolerances are way off the other way, your shaft won't even fit in the hole. So what tolerances do you need to achieve your functionality, right? And then 3, you also need to worry about how are you communicating your tolerances, right? We talked a little bit about that. When you dimension your device, how are you actually communicating your tolerances? Are you communicating them correctly? So beyond just this dimensioning problem, for the most part, when people communicate tolerances, what they'll do is they'll say on their drawing, right? So you create your drawing of your part, and you got a couple of views here, and you got numbers, whatever. And here's another view, and then here's another view. This doesn't make any sense, but whatever. And then down here, right, you have all kinds of information. You have your name, the part name, part number, and you can say all dimensions plus or minus, and you can give a general tolerance, right? And that tolerance, your general tolerance, is going to be pretty loose, right? Because this is the tolerance that your machinist is going to use when dimensioning all the parts, so it should be easy to achieve. Now, any particular important dimension, it's a dimension that has to have a certain tolerance for your device to function. You're going to give it on the actual drawing. So this dimension, like here, let's blow this up a little bit. Let's say we're giving this dimension right here, and it is 6.02 centimeters, right? And then we'd say plus or minus 15, or sorry, plus or minus 0.00, whatever it needs to be, right? Certainly it's going to have to be better than 0.001 centimeters. And you do that right on the drawing. That tells the machinist what kind of of tolerance you need. Now ideally, right, nothing will piss off a machinist more than you just giving a crazy tolerance and making them figure out how to do it. Ideally, you think this out ahead of time, right? You want to piss off Marco in the machine shop, you go down there with like 0.0001 tolerances, right? And you tell him, figure this out. No, you should think about it ahead of time. Can you mill this? Do you actually need to get a broach to pull through this hole to get the size just right, right? You need to grind it so that you can ensure that you get the highest tolerances possible. Okay, this matters quite a bit. You know, I had a design project where a group had to make a valve, right? And this valve, you start out with a large block of metal. You drill in holes that high pressure hydraulic fluid comes in and out, and in between is a shaft that moves back and forth, right? This fluid comes in and then comes out, or sometimes, depending on the location of the shaft, there's another hole here. The fluid can come in and go out this hole, right? So it's a valve that works by moving this back and forth. But you can imagine that if your tolerances are not very good, instead of this fluid coming like this, it can squeeze out between any kind of gap here and get out all over the machine floor, and you lose your hydraulic fluid and everything fails, right? So they had to pay very close attention to the tolerances that they were capable of and whether or not they were capable of making this valve, right? And this is why actually valves are relatively expensive, because you have to get the shaft and this hole just right so you don't lose a lot of hydraulic fluid. In any case, that's tolerances. I'm going to want to see some discussion of tolerances in your final report. Okay? All right.